All right, guys, this is topic 2.3, work, energy, and power. For this, you need your data booklet and a notebook. So we have from topic 2.3, work is equal to force times displacement times cosine theta. We have kinetic energy, E sub k equals 1/2 mv squared. We have potential energy. This is elastic potential energy. Elastic potential energy equals 1/2 k change in the spring's position x squared. We have the gravitational potential energy, the gravitational PE delta E sub p, the change in the object's potential energy, equals mg mass times the acceleration of gravity times the change in the object's position, vertical position of course. We have power equals force times velocity. And efficiency can be the work out divided by the work in, or the power out divided by power in. It's the useful energy out, the useful power out divided by how much power or how much energy had to go in. Okay, so determining work done by a force. Work, capital W, is force times displacement over which the force acts. This is the dot product. Work is equal to F dot S. Unit for work, Newton times a meter, which is the same thing as a joule. So work is a scalar quantity, and if the force applied to an object is not parallel to the displacement, the formula for the work has this minor correction, which is work is Fs cosine theta. F dot S, it's the same thing. Theta is the angle between the applied force and the displacement of the object to which you're applying that force. If the force and the displacement are parallel, for example, if I lift a book and I'm moving this book upwards, then I'm doing positive work to the object. Cosine of 0 degrees is positive 1. If F and S are anti-parallel, where theta is 180 degrees, then I'm doing negative work to the object because cosine of 180 is negative 1. Now I want you to try, maybe grab your cell phone or your notebook and support the cell phone or your notebook underneath on the underside, and then lower your cell phone or notebook down to the ground. You are now doing negative work to the object. When you do negative work to the object, you decrease the potential energy. Positive work, you're increasing the object's potential energy. All right, so let's talk about springs really quickly. Springs act to move an object in an opposite direction from where the spring was displaced. So we have this equation known as Hooke's law, and Hooke's law is F, the spring force, the force that the spring exerts on an object, equals negative Ks. S is the displacement of the object, K is the spring constant, and the negative sign just denotes that the object, the spring, tries to move the object in the opposite direction of its displacement. So if you pull a spring out, the spring tries to force the object back in. If you compress a spring in, the spring tries to force itself back out. This equation for Hooke's law is not inside your data booklet. Feel free to add it. I've never seen a problem where you've specifically needed to know Hooke's law, but just in case you want to do a Hooke's law experiment, this will be helpful for you. We have kinetic energy, which is the energy of motion. The bigger the speed, the bigger the E sub k. The bigger the mass, the bigger the E sub k. So kinetic energy, again, is 1/2 mv squared. Energy is a scalar. If you have positive energy, that means the object has gained energy. Negative energy means an object has lost energy. You can't have energy going to the right or energy going to the left. It doesn't make sense. It's just a gain in total energy or a decrease in total energy. The energy due to the position of a weight is called gravitational potential energy. The change in an object's gravitational potential energy equals mg, the object's weight, times its change in vertical position, delta H. Okay, so let's discuss conservation of total energy. If there's no friction or drag to remove energy from a system, the change in E sub k plus the change in potential energy should equal 0. If your change in kinetic energy doesn't equal the negative change in potential energy, some energy was lost to non-conservative forces like friction and drag. So you need to keep that in mind. This is only true when conservative forces are acting on an object. No friction, no air resistance. This is known as conservation of mechanical energy. Essentially, as a kinetic energy changes, let's say it increases, then the potential energy decreases. You know this if you drop an object from some height, it starts off with a very high potential energy and no kinetic energy, and as it falls, it's losing potential energy. It has a negative potential energy because it's losing it, and it gains kinetic energy. The total energy of a system never changes. And indeed, even for non-conservative forces, that energy is still there. It was just lost due to heat or deformation of the object. Work energy theorem. It takes work to change an object's kinetic energy. So work equals delta E sub k. This is the work energy theorem. To change an object's kinetic energy, you must do work. Now, fields, which we will get more into later, but fields like a gravitational field around our planet causes a negative change in an object's potential energy. So the work of fields equals negative change in potential energy. You know this because you don't have, if you let go of an object, you don't have to push it all the way down to the floor. It naturally falls because we are inside of a gravitational field. Everything experiences this force of gravity. As this field acts on an object, it decreases an object's potential energy. Suppose we have some oscillating pendulum or an oscillating spring, and we want to generate a graph of kinetic energy and potential energy versus time. This is what we would see. The energies, the kinetic and potential energies themselves also oscillate in time, just like what we physically see. The kinetic energy plus the potential energy for an oscillating system equals the total energy, and it's constant in the absence of drag or friction. Finally, power is a rate of energy transfer. Just because it's a rate doesn't mean it is a vector. It is still a scalar quantity. So from the formula, we can see that power has the units of energy, joules per time, joules per second, and a joule per second is also known as a watt, capital W. Don't confuse it with work. Power can also be equal to force times velocity, the dot product. So power is still a scalar quantity. Thanks for watching and study well.